So I know some of you are going to say this is nuts, but I'm using a pair of bright red LEDs as a pair of Varactor diodes, and back to back, right? Cathodes together on the tune, reverse biased, putting out a nice steady signal, good sine wave. Now the only problem with this is they do not have a lot of range. I'm only getting about 9 kilohertz end to end and very non-linear. But I just wanted to show you that you can use something like an LED even as a Varactor diode. In this final session we're going to go over the Varactor diode, or as it was once called, the Varicap diode. These were well known by the mid-60s, and all of the various tricks for compensating them both over temperature and over frequency were understood probably by the late 60s. So being used in ham radio projects, it was fairly new, probably starting in the 70s and 80s, but some of the early AM radios started to use Varactor diodes probably in the 70s and 80s as well. And this one here, this part is equivalent to a 365 picofarad variable capacitor. So this has a lot of interesting uses, both with ham radio and with radio projects in general. So there's no community that loves to use avant-garde and low-cost type solutions rather than using the proper parts than the radio builders and experimenters on this YouTube channel. We really would like to use the floor sweepings, the low-cost garden variety parts that cost a few pennies each, or we can scavenge off old circuit boards. And we take ATX power supplies apart, old radio and computer boards, and scavenge some fantastic reused parts off them. So the first question that comes to mind is, can we use ordinary power diodes like these as tuning elements, as Varactor or variable capacitor diodes? And the answer is, everybody does it. At one time or another, you're going to have somebody that's preaching. I used a couple of 1N 4003s in parallel on the bottom of a crystal, and I got a beautiful VXO out of it. I was able to warp it a couple of kilohertz, and it worked great for my QRP rig. Absolutely true, it works fine. However, in a high performance VFO, like we're trying to build, where we're trying to keep things down to a few hertz of change over temperature, you're going to find these diodes are not going to work anywhere near as well as a proper modern Varactor diode. So the first thing we're going to explore is, well, can you use them for anything? Yeah, can you use them possibly as a temperature sensing element? Okay, now I have a 1N 4001, your favorite diode, connected with a 5-volt bias through a 100K resistor, and it's bypassed on the bottom to ground. And let's put some heat on the 1N 4001 and see which direction it goes. Okay, it's definitely negative temperature coefficient. As I heated it up, the frequency went up. As you can see, it's rapidly coming down now as it cools. So the lowly 1N 4001 diode. Now you've all heard of using a 1N 4001 or a pair of them as a Varactor. They have a depletion region, and if you reverse bias them, you can use them as a tuning element. Okay, it not only went up, it caused the oscillator to stop working. So the Q of this diode is causing trouble alone. Very low Q compared to a proper Varactor diode like the BB910. In fact, the amplitude is about half what we saw with the proper varactor. Now if we put some heat on this thing, like the tip of the soldering iron underneath the diode, watch what happens to the amplitude. As you can see, eventually the oscillation goes away, and it's recovering now as it cools down. This is characteristic of a very low Q type tuned circuit. So folks are going to use power diodes as varactors, and that's just the way it is. It's great for little hobby projects where you only need to change capacitance, to do fine tuning. Now, if you want to use a proper varactor diode but not spend a lot of money, I suggest the BB910 series developed for VHF and UHF TV tuners. This thing has a very linear response and a nice range between 40 picofarads down to just a few picofarads. So it's a very useful diode. You'll find this diode used in a lot of those little FM radio kits that you build yourself. So it's made in mass quantities in a plastic package that we can easily use. The amplitude, now that I have the proper varactor diode on there, is much higher. What does that mean? It means very simply that the BB910 varactor has a much higher Q than the 1N4001. Another factor you need to consider. The 1N4001 is not a proper varactor. It has a very low Q. It will affect the output amplitude, and it will affect how much feedback you need to keep your oscillator stable. Now the BB910 with 5 volts of bias through our 100K resistor should have a capacitance of around 15 picofarads with that 5 volt bias. If it is positive coefficient, then it will start to increase in capacitance, and that would be equivalent to the bias voltage getting lower. Okay, remember the capacitance goes up with the diode as the voltage gets lower. Also, this is a semi-log plot, so you can see that this can be corrected fairly easily using a logarithmic potentiometer like a audio taper, or a synthesized audio taper using a network like this. Okay, so we need to use the heat gun to establish if it's a positive or a negative temperature coefficient with this BB910 diode. It's definitely a positive coefficient. Isn't that interesting? Just the opposite of the 1N4001. The varactor diode is always operated under reverse bias, which creates a depletion zone around the PN junction. A varactor is always operated before forward bias conduction and at a lower voltage than reverse breakdown. Changing the level of the reverse bias changes the thickness of the depletion region and thus the effective capacitance of the diode. Increasing the voltage causes a decrease in capacitance, so an increase in the reverse biased voltage increases the thickness of the depletion region and reduces the capacitance of the varactor diode. Lower reverse bias equals higher capacitance. Varactor diodes are specified with a nominal capacitance value and the range of capacitance that can be achieved with a maximum and minimum voltage level. Increasing the bias voltage range increases the capacitance range available, but designers can look for varactors with larger capacitance to voltage ratios. The capacitance ratio of the varactor diode is also called the tuning ratio. This ratio is basically the lowest capacitance to the highest capacitance based on the bias voltage. Tuned circuits employing Varactor diodes exhibit a nonlinear frequency versus control voltage characteristic. They require a larger voltage change to tune high frequencies than they do at low frequencies. Modern varactors are more linear and require less correction. They also operate at much lower voltage ranges. In the early 1970s, hyper-abrupt silicon varactors became available, in which the capacitance to voltage curve of the abrupt junction diodes was modified by adding an N+ layer under the junction, either by ion implantation or by an additional diffusion layer. This had the effect of increasing the capacitance ratio and improving the linearity of the frequency voltage curve. Varactor tuning bias can be DC from a variable regulated voltage source, or DC produced by a digital analog converter, or integrating pulse, pulse width, sawtooth waveforms, or even digital words. Two common hookups are used: the single diode with coupling capacitor and the dual back-to-back hookup. The dual topology reduces the temptation of forward bias. This is called the large signal effect. Intermodulation and forward biasing fears are out there. The dual hookup cuts the tuning range since it puts the two varactors in series in respect to the inductor. The dual hookup is preferred in loop antenna and preamplifiers that might see high signals. So if we use the single varactor hookup in our circuitry, such as in a receiver or transmitter, and RF sneaks in, forward biasing the diode could cause harmonic and intermod mixing distortion. However, if the varactor lives in a well-shielded and buffered VFO box like we have, with a known steady voltage swing, the single diode hookup may be acceptable. There are other hookups that can help to eliminate this effect, namely the push-pull or balanced VFO topology. The next logical step with the VFO is to convert it to Varactor tuning. So you'll notice I have a way of holding the variable capacitor back from the front for the vernier dial. There's some cleverness to this as well, because I knew I was going to be replacing the variable capacitor with a potentiometer to tune the varactor. So I've got it placed strategically so that I can replace the tuning capacitor with the pot, and the vernier dial will still work. The tuning range is extremely similar to the small capacitor that I'm using, and because we have such a large fixed capacitor on the VFO, I think the linearity is going to be excellent and very little correction will be required. And one more thing, because adding the varactor to the already positive coefficient toroid coil, I think we're going to have a very powerful positive temperature compensation built in. So I think we're going to get away with just using a negative compensation capacitor on one trimmer. So I was thinking of using a 12-volt regulator separately to allow me to have a nice wide tuning voltage for the varactor. But instead of just using a 7812, which is a fairly noisy regulator, I decided to go with a precision regulator based on the TL431 shunt regulator, which is a basically a current mirror style regulator. And there's a lot of really cool application circuits for this. So where do you get one of those? Well, you can order one, or most of these old ATX power supplies have things like that on them, and I found one right here. So most of these supplies are going to have these TL431, 432 chips all over them. So just get one of these old power supplies and find one of these little handy regulator chips, and let's see if we can build something up that'll give us maybe 9 or 10 volts, a very nice clean supply for the Varactor tuning. So some practical limitations with using a potentiometer instead of the variable capacitor. The potentiometer is a 270-degree rotation device, and our vernier dial is a 180-degree rotation device. So we're going to lose some of the rotation on the potentiometer. And that means that we're going to have to think very carefully about what part of the potentiometer we want to use. Now this depends on which end is positive and which is negative, and where on the varactor curve we want to operate. So it could actually work to our advantage if we're careful the way we set up the potentiometer. So the TL431 circuit, very simple. It's basically a shunt regulator, like a super zener, but well regulated. And you can use this 100K pot we have here to basically go as low as the reference voltage, and we can bring that up slowly. And you can set this for whatever our target is going to be, something like 11 volts, and we can adjust it once it's in place. So let's take a look at the range. I have the two varactor setup, the anti-parallel or the dual varactor setup, kind of haywired in. They're not dressed down like I'm going to put them eventually, but they're kind of flying in midair. I have one varactor going up to the hot part of the tank and one down to ground over here, and then the 100K feed off the pot going to the middle. But you guys can see that pretty easily. So what do we have on the potentiometer? Okay, we've got that original 11 volts that we programmed. That's fine. And the other side should be ground. It is. So let's look at our tuning voltage. Looks like we're at one end at 0.5. And we're going to go all the way as far as we can on this potentiometer. Remember, we're only using a little bit of the pot. Instead of the 270 that the pot can do, we're only doing 180 to 7.57. So 0.5 to 7.57. If you look on the chart, 0.5 would be 2, 3, 4, 0.5, and 7.5 is 2, 3, 4, 5, 6, 7.5. That's a very nice range. My heavens, we're lucky on this range. That's just about perfect. I'm not going to change anything. Is it tuning up or down? Let's look at the counter. Okay, we are at the 0 scale, and we're going to work up. Oh, we're going the wrong way. Okay, not quite 100 kilohertz tuning, but plenty. So we need to flip the leads on the pot, but I think we got a good thing going. The sine wave's beautiful. The output power is great. I'm going to call this a winner. And also notice it's not drifting. Just a little bit. Okay, so now we can evaluate how the dual varactor compares to the original trimmer capacitor that we removed. We can see that the trimmer was fairly linear, with 30 kilohertz to the 50% point and 30 kilohertz to the 100% point, covering 60 kilohertz approximately in both cases of the cover off and the cover on. With the varactor cover off, we're getting about 70 kilohertz, so actually a wider range, but it's not as linear. We've got 43.5 kilohertz to the 50% point on the low frequencies, but on the high frequencies only 26.79. So like we said, it's a little more difficult to tune as fast a rate at the high frequencies because the voltage is less effective up there. Changing voltage gives a much less capacitance change when you're at the low capacitances with a varactor. So we can possibly try to linearize this by putting a bias resistor across the potentiometer to try to give it a quasi-logarithmic effect to try to zero this out so that it's at least a little more linear across the range. So I just flipped the leads on the pot so that it tunes in the right direction. So as you go from 0 to 100, you go from low frequency to high frequency. The problem is, though, the voltage that the potentiometer is putting out is different now, and it's going up to 10 volts instead of around 7.5 that we had before. So now we have to loosen the shaft on the to the pot and readjust the pot so that we get that same range we had before when the pot was wired backwards. I've used the little Allen wrench. I moved the pot till it's at 7.5 volts, and now we're back at 5218 where we were before. Okay, we're now back to our 70 kilohertz. It's tuning the right direction, and notice that the frequencies are very close to the cover-off original frequencies. Again, the toroid coil does not react to the cover coming on and off as much as the air coil did, that's for sure. I'm very impressed with the room temperature stability of this thing. I mean, it hasn't even been 5 minutes. This thing with the dual Varactor hookup and the stable regulation of the TL431. The leads are dressed down a little bit better now, better grounding. And with the cover on, I am very satisfied with the stability of this VFO. So I think we've proven that we can use a toroid inductor and Varactor tuning and end up with some excellent performance, replacing some of those expensive variable capacitors. Right now, neither of the comp capacitors are attached. The two trimmers are just sitting in there. I can do a single Varactor hookup before we end the video, just so you can see what a single Varactor looks like. See if that affects the amplitude we're seeing or the frequency range. It should actually make the tuning wider. Maybe it will affect the temperature stability. Maybe having those two Varactors back to back has some type of temperature stabilization effect. Hard to say. But I'm very satisfied with what we're getting here with Varactor. So just for fun, I hit the plate with the heat gun to see what the effect would be. And after about 3 minutes, the frequency started to go down. I think we can surmise that this is positive temperature coefficient as we thought. In other words, the value of the capacitance, the effective capacitance, is going up. A combination of the Varactor positive coefficient and the coil and copper. So I think I will hook up at least the negative compensation capacitor trimmer, and we'll leave it at that. Again, I don't have the right equipment to do a full compensation on this oscillator, but I do have the equipment to be able to arm it with the proper components to compensate it. And nothing beats starting in a good place and getting stability with no compensation, that's for sure. The more stable you can make it out of the box, the better. So the original curve shows definite, looks like an x squared or perhaps an antilog, some type of polynomial curve with the tuning. And we need to correct that curve. I tried to do curve fitting and figure out what the function was on the curve. It looks like it could be corrected with a log or perhaps something like a log curve. And more related to an x squared type curve than a log curve, but I think it can be done with the pseudo-log hookup on the potentiometer that we've heard about. And I'm just going to go with a with a n times 2 type correction. So it's a 20K pot, and I have a 10K resistor from the center to ground. That's going to give me a correction that should be opposite of that curve. The other thing we can fool with is the actual range of voltages that we're going down, and by biasing it closer to the bottom, I think we can balance it out so that the tuning increments remain fairly steady across the dial. Right now, we've got like 38 kilohertz happening down at the low voltage side, and at the higher frequencies, we have problems tuning as much. It's down, around 19 or 20 kilohertz. So it's way uneven and non-linear on the dial. We'd like the dial to be as linear as possible. So this correction should hopefully help that all out, and we should have a more linear solution. It starts with taking data, and I'm just doing it every 10 increments on the dial, and reading the voltage on the meter and the frequency on the counter, and you just plot all of that and then see if your correction has taken hold. The other thing we can do is we can spin the pot to try to operate at different points on the curve to see which gives us the most linearity with the dial. So I think we picked up a lot of linearity here, and we're almost perfectly balanced at about 29 kilohertz each side of center. Now here's where we started, and I think we've straightened the curve a little bit here. We did lose a little bit of tuning range, however. There was a price for our linearization. We lost some of our tuning range on the potentiometer, and that's normal because we're loading part of the potentiometer a little more than the other, and we did shift the voltage range down a little bit. So anyway, the next thing we'll try is a single varactor tuning, and then we'll be done with varactors. For the single tuning, we removed one of the varactors and replaced it with a 1000 picofarad C0G capacitor. Let's take a look and see how the tuning is affected. Quality of the signal still looks excellent. Let's see how much tuning range we have. We should have just about double the tuning range with that varactor removed. So all I'm going to say about the single diode is that the curve is a little bit tougher to correct because it seems to have two distinct regions. Looks like kind of a linear region and an exponential region. And it covers more range, almost 75 kilohertz compared to the dual diode setup. So this was my best effort at trying to compensate the single diode. I got this far by increasing the bias range from a half a volt up to a little over 2 volts, 2 volts to 9 volts, and then I used a resistor across the pot of 68K, so just a little bit of compensation. You can see it in the voltage chart that I was synthesizing, lower voltages in the area where the diode's more sensitive, and higher voltages where the diode is less sensitive, to try to straighten the curve, so to speak. But a little more difficult than compensating the dual diode setup. So I hope you've enjoyed this series on VFO construction and using FETs in a cold pitch circuit. If you really want to learn how to build a VFO, I think we need to go back to the old BC221 frequency meter. They knew how to do it back then. This is probably the best designed VFO I've ever run across, and it was done in the late 30s and used all during World War II. So if you'd like some interesting some interesting videos. Check out my video on the BC221 frequency meter, and I think you'll learn more than you learned on this solid state stuff.